The first question, answer yes. Yeah. Why? Let me explain. Yeah. Several students couldn't see why we can do this. Yeah. One can find a set of non-zero, find non-zero coefficients. That means you need to consider special case, not the general case. Yeah. So this tells us we only need to get a special coefficients. Special coefficients, not a general. General, then you use Horner's rule. Yeah. But special, then we can take advantage of the structure. Yeah. Here, the structure, yeah. So I hope you can connect to the Pascal's triangle. Yeah. You need to quickly connect to the Pascal's triangle. All right, yeah. Degree 6. Yeah. So based on Pascal triangle, 1, yeah, 1 here, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Then the line we need to use here, 1, 6, 15, 20, 15, 6, 1. Yeah, I hope you know how to get these numbers, yeah, based on the property. Yeah. So that means if you choose the special number here, 1, 6, 15, 20, 15, 6, 1, then this polynomial becomes 1 plus x to the 6. To calculate this polynomial, one addition here. After that, 3 multiplications. You take 1 square, then square multiplies itself 2 more times. So total 3 multiplications. Square the first time. After you have square number, you do cube, right? Cube. So you multiply the square number, multiply itself 2 times. Yeah. 2 more times. Yeah. 2 more multiplications. So you get 3 multiplications. Yeah. Yeah. So you need to have the knowledge, several pieces for this question. Yeah. Pascal's triangle. Yeah. So then, after you get this formula, you can use 3 multiplications to find this number. Yeah. All right. The second one, 8. So you can find the formula. The formula flow function, yeah, flow function because we can use approximation. Yeah, we can remove the flow function. Yeah. This one, 8. Yeah, 8. Yeah. So I think you can see it. Log, double log. Yeah. Log. So you know how to compare log. Yeah. But this another log function, make it even smaller. Yeah. Yeah. For two other options here, only 1 log, right? Yeah, 1 log. Yeah, 2 logs, much smaller than 1 log. Yeah. Number 4, yeah, because this number is slightly greater than 1. Yeah. So then we have our exponential function, we have that result. Yeah. A few students pick B. Yeah. Yeah, also yes. Euclidean algorithm. Yeah. We can avoid using prime factorization technique, Euclidean algorithm. 6B, remember in class we compared that number. Yeah. Yeah. In class, so that number, this number approximately equal to 2 to the 63, right? Yeah. Approximately that number. Yeah. But 80 disks 2 to the 80 minus 1. Yeah. You just look at the dominant part, 2 to the 80. Yeah. Much larger than the number of sands on Earth. Yeah. Number 7, many people miss this one. Yeah, many people pick A, B. Yeah. Answer is D. Answer is D. Yeah. So I saw some students plugging numbers, but still couldn't get a correct answer. If you plug in n equals 1, all correct. Yeah. All correct. Because when I make these formulas, I use 1 to check. Okay. Yeah. So make sure all 4 options for n equals 1, all correct. But for 2, 3, then it will be different. Yeah. And in module 1, actually, I give you the formula. Yeah. I'll give you this formula in module 1. Summation consecutive cubes, I said 1/2 n times n plus 1 squared. Okay? Yeah? So that formula. Because this is the summation of consecutive integers. You just take that formula, do square. Yeah. 1/4 n squared n plus 1 squared. Yeah. And here you need to multiply 8. Right? Yeah. 2 cubed can be factored out. So you need to multiply 2 cubed. That's 8. Then you get 2. 2n squared times n plus 1 squared. Yeah. Yeah. So this one, many of you missed this question. All right. Number 8, true. Yeah. Number 8, this time I give you n greater than 5. Yeah. If you fix 3 elements in place, remaining 2 or more, right? Yeah. 2 or more. Then you can make them, use that rotation way, you can make them all out of place. Yeah. Yeah. So different from our homework question. Yeah. This time, yeah. Yeah, more than 2. Yeah, actually the remaining, because n strictly greater than 5. Yeah. So you can do that rotation way. Yeah. B. Yeah. Yeah, because x2 greater than 3 elements. Yeah. Number 10. Yeah. Number 10 is B. Yeah. 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 Let me explain a little bit. Yeah. use our homework question as the starting point. Yeah, but you need to modify slightly. Yeah. First, you write the factorization similar to our homework question factorization, Horner's rule factorization. A0 plus x squared factorization. A1 plus the next round factorization, this time x cubed A2. Then x to the fourth. This is the factorization. Yeah. You can see the power function that we factor out, x squared, x cubed, x fourth to the x to the fifth. They have different exponents. So when you do preparation, you need to calculate all of them. That's different part. Yeah. For our homework, we only need to calculate x cubed and x to the fourth. Yeah. But here, you need to calculate these four numbers, x squared, x cubed, x to the fourth, and x to the fifth. Yeah. The first round preparation, you need to use one multiplication to get x squared, another one get x cubed, another one x to the fourth, another one x to the fifth. Yeah. So in your preparation, you need to use 4 multiplications. Okay, that's the first round. Second round, now you can plug in these 4 known numbers into our factorization formula. Yeah. The first multiplication, x squared and the parenthesis. Second multiplication, third multiplication, last multiplication. Okay? Yeah. So another 4 multiplications. All right? Yeah. So 4 plus 4, you get 8. 4 plus 4, you get 8. Yeah. Yeah. Right. Yeah. Quite some students miss this question. Yeah. Yeah. So here you can see, in order to do it correctly, you have the background, right? We did several similar questions. That's our background. With the background, you need to have good understanding. Yeah. So you need to, so you can manage the knowledge pieces in your background and use your knowledge in the right way to get this answer. Yeah, think about it. So the understanding is very important. Yeah. Yeah. All right. Yeah. Yeah. So that's the first 10 questions. Yeah. So let's only do the first part today. Yeah. So remaining, let's do the next time. Yeah. I already I have the solutions, so I can post the solutions. Yeah. Next time, I only pick selected questions. I do not go through all the questions. To save time, I only cover relatively hard questions. Yeah. And for the answers and solutions, you just study my solution file. Okay, yeah. All right, so that's the first part, the midterm. Yeah. Then, let's go to the new part today. Yeah. Fibonacci numbers. Yeah. So in this topic, we can learn more properties, more understanding on the recursive algorithms. C.1, Introduction to Fibonacci numbers. Problem number 11, calculate Fibonacci numbers. Given recursive formula, first two numbers, f0 equals 0, f1 equals 1. Then we do recursion. Fn equals fn minus 1 plus fn minus 2. So it's a very simple Fibonacci formula. Yeah. We want to find the Fibonacci numbers f sub n. Yeah. Given n number, then you need to calculate the Fibonacci number generated by this recursive formula. So very simple. So you can write a program quickly, right? Yeah. So here, because we need to understand the recursive algorithms, the problems, so we want to avoid, yeah, so here, so we need to study this question in a very deep way. Yeah. All right. Yeah. First, let's look at a few Fibonacci numbers. Yeah. Yeah. All right. Yeah. 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 So the reference. Yeah. When we solve it, yeah. So we want to solve it in different ways. So the first way, solve it algorithmically. Yeah. So we want to use some simple algorithm to solve it. Okay? Yeah. So you can call it brute force first. Brute force method first. Yeah. So yeah. Just do it directly. Yeah. Without any technique. Yeah. So let's write a program to implement some algorithm. The second way, we want to solve it mathematically. Yeah. Mathematically, our goal, we want to get a formula. If you can find a math formula for the Fibonacci numbers, then you just plug in the number into this formula, you get the answer immediately. Yeah. So that's the second way. Yeah. All right. The first way, yeah, look at this recursive function implementation. Yeah. Very straightforward. Yeah. Very easy to write, right? Very easy to write. Yeah. Fibo, yeah. You pass this input n number, yeah. For the two base cases, return, yeah. 4 and greater or equal to 2, then you need to do recursion. Yeah. Returns a number. So what number to return? You put this recursive function call. Yeah. After you get the sum of two recursive function call numbers, you return that sum number. Yeah. First, very easy to see it's correct. Right? Yeah. First, this function should return the correct result. Yeah. But the second question is how fast it is. Is it a good implementation? Can we improve this implementation? Can we make it faster? Yeah, that's something we need to understand. Yeah, how fast it is. All right. Yeah. Okay. Yeah. So let's study. Yeah. Try to answer these questions. Yeah. All right. Yeah. So if, yeah, actually, because our project 1 will be due soon, yeah, then I will assign project 2 quickly. Yeah. By the end of this month, I will assign project number 2. Then we will calculate Fibonacci numbers. We will use several different algorithms to calculate Fibonacci numbers. Yeah. This one is our first method. So you will see very slow, extremely slow. Yeah. Yeah. Horrible implementation, too slow. Yeah. You will see. Yeah. When you do experiments, yeah, when n equals some number actually not very big, yeah, when this n greater than 40 is not a big number, right? 40 is not a big number. But when n is greater than 40, you need to wait pretty long time to get an answer. Yeah. Dozens of seconds. That long. Dozens of seconds. Yeah. Oh, yeah. So that means it's very slow. Why it is so slow? Yeah. So we will see it. Why this method is so slow. Yeah. Here I want to draw a recursion tree to show you why it is so slow. Okay, yeah. Let me use a relatively small number as the input number. N equals 6. This number very small. Yeah. But you can already see the problem. Yeah. If we draw a recursion tree, you can see the problem. Yeah. Because here we use the recursive function. Remember, I explained the recursive function internal implementation in computer memory. We use a stack, right? Stack. Yeah. So when you make the first function call, Fibo of 6, it's not available. If it's not available, this number is pushed into the stack, f of 6. Push into the stack, okay? If that's not available. So then, do recursion. Now, you need to find a Fibo of 5 and a Fibo of 4 before you can find Fibo of 6. But Fibo of 5, Fibo of 4, not available, so you push them into the stack. fiber of 5 and a fiber of 4 push into the stack, and so on. Okay? Yeah. So internal implementation like this. Yeah. But to get fiber of 5, you need to do another round recursion. So fiber of 4, fiber of 3. Yeah. This side, fiber of 3, fiber of 2. Okay? So you keep doing the recursion. Then, when you reach the bottom level, this is the bottom level. Okay? The bottom level, because at the bottom level, these fiber numbers are given. The base cases, 2 base cases, fiber of 0, fiber of 1, given. Then you can do the calculation starting from the bottom level. Then you can move up. So in the stack, you do the calculation from the top part. Top, the base cases, you can do the calculation. Then you keep popping up the unknown numbers in the stack and do the calculation. Yeah. Eventually, you reach the bottom, you do the calculation, you do the final, you get a final answer. Yeah. That's the internal implementation. Using stack to implement recursive function call. Okay? Yeah. So based on this diagram, can you see what's the problem? Why our first method is so slow? Yeah. So based on what do you have seen here? Yeah. So what's the problem? Why the method is so slow? Okay? Yeah. Look at the redundant computation. Redundant computation. Can you see the redundant computation? How many times you need to calculate fiber of 2? How many times you need to calculate fiber of 2? Then fiber of 3, fiber of 4. Lot of redundant computation. Yeah. Okay? Yeah. So for fiber of 2, look at, in this small example, you need to calculate 5 times. 5 times. But you only need to calculate once to get a fiber of 2 number. So if you calculate 5 times, that means 4 of the 5, that's the redundant computation. Then you can imagine when n is a large number, how many redundant computation you need to calculate. Yeah. For example, when n equals relatively large, not too large, equals 100. 100. Yeah. The tree is big. Yeah. How many times fiber of some number, you need to do a lot of redundant computation. That's the reason it's so slow. Okay? How to fix it? How to fix this problem? Think about it. Straightforward thinking. To fix this problem, can you remove the redundant calculation? Remove the redundancy. Okay? Each intermediate Fibonacci number, you only need to calculate once, not more than once. If you can use some special method to control each intermediate Fibonacci number, you only need to calculate once. Then you can improve the performance significantly. Yeah. You can make it much faster. Only calculate once. So that's the solution idea. Like how to make it faster. All right. Yeah. How to improve the algorithm. Method 1. Iterative algorithm. Because we know if we use iterative algorithm, we do not use stack implementation, right? If we do not use stack implementation, then we can save memory resource. Yeah. So that's our first option to improve this algorithm. Yeah. Yeah. Iterative, then we do not do recursion. Yeah. So we just use a for loop. So we can calculate. Yeah. All right. Yeah. So after f of 0, f of 1, then we calculate f of 2, 3, 4, moving up. Every time, every iteration, we calculate 1, right? Yeah. This way you can see only once. This way, there is no redundant calculation. Yeah. So you can see this way, it should be much faster than our first method. No redundancy. Okay? Yeah. Yeah. See, you can get an idea. Okay? Yeah. But this way, we get out of the recursive algorithm. This implementation, we do not use recursive algorithm. Okay? Yeah. Yeah. So that's sometimes if you want to avoid some drawbacks of the recursive algorithm, you can consider iterative method. But this idea, there is limitation. There is some limitation in this method. So what's that? Because we know the reason that we use recursive algorithm because we want to take advantage of its power. It is very powerful. If you get out of recursive algorithm, then at the same time you lose its power, right? Yeah, that's not very good. Yeah, because sometimes, especially when the problem is very hard, so you need to use a recursive algorithm. Its power to solve it. Yeah. So here the question is, can we still use the recursive algorithm but remove the redundant computation? Okay? Yeah. So that's our next improvement. Yeah. We want to use recursive algorithm because we know we need its power. Okay? Yeah. Otherwise, we cannot solve many hard questions. Yeah. All right. But you have to find some smart way to remove the redundancy. Yeah, think about it. Then here, there is a very important idea in computer algorithms. Yeah, so here I use this simple example to introduce a new type of algorithms. It's called a dynamic programming. Dynamic programming idea, approach. Yeah, it's very important in computer algorithms. Yeah. So let me explain its idea here. All right. Method 2. Yeah. All right. So we do not change recursive algorithm. So we use the recursive algorithm, but we modify. In our original recursive algorithm, a lot of redundant computation, but this time we need to find a smart way, simple way. It must be also a simple way to help us avoid redundant computation. Yeah. So what's that? Okay, yeah, all right. So here, yeah, think about all the intermediate computation generate intermediate results, right? Intermediate results. So here we need to find a way, efficient way to manage our intermediate results, manage our data. Yeah. Intermediate results, that's the data we need to manage. Yeah. Can you find convenient, clean way to manage your intermediate data? No. So here, we design some effective way to do the bookkeeping on our data. Okay, we do some efficient bookkeeping way on our intermediate data. How about that idea? Okay, how do you control your data? When you control, when you detect if it's a redundant computation, you reject it. How about that? You do not do it. If you can detect it is a redundant computation, you don't do it. You don't do it. Because you already have the answer the first time you do the computation, right? You don't need to do it the second time, the third time. You never need to do more than once, right? That's the bookkeeping. Bookkeeping allows you to do that. Okay, all right. How to do that bookkeeping? Use an array to store calculated values. Those intermediate values, after you do the calculation, store them in an array. Do not throw away. Okay? Store them in an array. Yeah. Okay? Yeah. Then, if you store them in an array, then the next time you need to calculate one of the numbers in the array, you know it is a redundant computation, right? Because it is already there. Why you need to calculate the second time, the third time, and more? Yeah. So that temporary array allows you to see if it is a redundant calculation. If it is, don't do it. Reject it. Okay? If it's not, if it is the first time you do the calculation, then do it. Okay? After you find that number, store it in that array for future use. Okay? Yeah, that's the idea. Okay? All right. Make sure that no value is calculated more than once. Yeah. With this temporary array, you can make that happen. Okay? That's the bookkeeping way. Okay? And this method, we call it dynamic programming. So it's a very important idea in computer algorithms. Dynamic programming. Okay? Yeah. Here, I use Fibonacci number as an easy introduction to the dynamic programming. Okay? Yeah. So it's in chapter 8. Yeah. But for this class, I can only introduce this idea, dynamic programming, here. Yeah. Yeah. Okay? Yeah. All right. The essence of dynamic programming, no repeated calculation. Yeah. Each number, here it's a Fibonacci number, each one only calculate once. Then you have its value, you store it. The second time, You just return the known value. How about that? You don't do the calculation. You just return the known value immediately. That's the idea. Okay? All right. Method 2. Now, we want to use the dynamic programming to write our recursive algorithm. Okay. Here, let me show you how to avoid redundant calculation using a temporary array to store the intermediate results. Okay. All right. And it's also called dictionary method. Yeah. Yeah. Here, first, this word programming, yeah, this word, it's different from our current programming, that meaning. Okay? You write a program, so you do programming, right? And that's the meaning. But dynamic programming, the programming here has different meaning of our usual programming. Okay? This programming we use its old meaning, history meaning, that programming, that's doing the tabulation. You make a table, okay? You organize your data in a table. So that kind of activity, so we call it programming. Okay? Here, dynamic programming, that means you arrange your data in a table. That method, because your data is dynamic. Okay? So we call it dynamic programming. Yeah. Tabulation. Yeah. All right. So that table you use to organize the data, you also call that table dictionary. So you organize data in a table, so we treat that table as a dictionary. Yeah. Why? Because you use the table just as a dictionary, right? Yeah. How do you use a dictionary? You look up words in a dictionary, right? Yeah. Yeah. So you need to use some method. Yeah. Look up words in a dictionary. But here, we look up Fibonacci numbers. We look up our data in a dictionary. We organize our data in a table as a dictionary, and later we need to look up in our dictionary if a particular number is already known or not. If it is known, we just retrieve it from the dictionary. If it is unknown, then we do the new calculation. So that's the reason we also call it dictionary method. Yeah. All right, yeah. So here, let's look at the implementation. Yeah. All right. This is the code. Yeah. In our implementation, you can see we modify our original recursive algorithm by adding the temporary array. This is the temporary array. This known f. Yeah. So from its name, you can see what's the purpose to use this array, temporary array, dictionary. This is our dictionary. Okay. Yeah. No, initially, the values, all the values in this array, all 0. 0 means the Fibonacci number corresponding to that location is unknown. So initially, yeah, only F0 is known. F1 is known. Other than these two numbers, all the remaining numbers all unknown. So you need to do the calculation. Okay? Yeah. How to check if a Fibonacci number is known or unknown? You look at its value. If it is 0, then it's unknown. Yeah. other than the two base cases. Yeah. Because when you do the checking, you consider the cases above the base cases. Yeah. So for a non-base case, if the corresponding Fibonacci number is unknown, then you look at the value greater than 0 or not. If it is greater than 0, that means it's known. If it's known, you just return the value directly from the dictionary, right? To avoid another redundant computation. You return immediately. Then it's very fast. You return a value from an array, it's very fast. Okay? Yeah. If it is unknown, then you move down. The next line in your code, yeah, check if it is one of the two base cases. Yeah. If it is, also return. If not, then you move down to do the new calculation. All right, yeah. I greater than 1, yeah. All right, yeah. Greater than 1, yeah. S equals Fibo of recursive formula. Yeah. Yeah. So you calculate. This time you use the variable S. S, yeah, to do the calculation. Okay, yeah. You can get this number eventually, right? After you get this number, before you return this number, store it in the temporary array first. Make that assignment first. Assign S to non-F at location I. Store it in your dictionary. After that, then you return its value. Because next time, when you need the value at the same location, you just return it directly. So you can see, after the small modification, then you never need to calculate one particular Fibonacci number the second time, right? Never. So this way, all the redundant calculation can be avoided. Yeah. No redundant calculation. Yeah. So this way, this is the dynamic programming method. Yeah. Try to, yeah. So the idea is not very complicated, but very useful. Very useful. Yeah. In your future programming, when you implement your recursive algorithms, think about, first, if you have any redundant calculation. If you have, use dynamic programming to avoid it. Yeah. All right, so then you can make it much faster. If you can eliminate all the redundant calculation, you can make it much faster. Yeah. All right, so this method, in our project number 2, you also need to implement this method. Okay, yeah. All right. C.2, golden ratio. Yeah. Because in order to calculate the Fibonacci number, we want to find its math formula, we need to use this golden ratio, special, constant. Very famous golden ratio. I believe you heard of it. Very famous golden ratio. And it is closely related to the Fibonacci numbers. Yeah. All right, so let's look at the golden ratio. Yeah. So, in ancient Greek times, yeah, people already know the special number. Yeah. Related to, a lot of things. Yeah. So here the painting, so the scale, ratio, different parts of the figure. Yeah. Some people argue. Yeah. So if you make that golden ratio, to use that to control the different parts, so then you can make the painting, the figure look natural. Yeah. Some argument like that. Yeah. Here you can also see some interesting property about the Fibonacci numbers. Here we use the Fibonacci numbers. Okay. Yeah. So here the number is very small. Yeah. But you can see the Fibonacci number. We use each Fibonacci number. We make a square. The side of the square is the Fibonacci number, f of k. Okay? Yeah. So then we draw those squares and we arrange them in a perfect way. Yeah. So you can see from inside this small square Fibonacci number with value 1. Actually it's f of 1. F of 0 is 0, so then we do not draw square. 0, no square. Okay? Then f of 1, side 1 square. F of 2 also 1, so another side 1 square. Okay? Then f of 3, 2, side 2 square. Side 2 square. So you draw side 2 square. But you can arrange the first 3 squares to make a rectangle. Yeah. Then the next one, f of 4, 3, side 3 square. Then you can fit in a nice way another square, fit them to get a new rectangle, and so on. Next one. All right. After this special way, you arrange the squares. All these squares corresponding to different Fibonacci numbers as their sides. Okay, not the area, the sides of these squares. Then you draw quarter arc. Quarter arc. Each square you draw quarter arc. Okay, so here quarter arc. Okay, yeah. So you get a nice spiral curve. Yeah. So things with a lot of interesting figures you can generate related to Fibonacci numbers and the golden ratios. Yeah. I remember I saw a book in the library, small booklet. Yeah. Describe many interesting stories and a lot of figures related to Fibonacci numbers and the golden ratio. Yeah. All right. First, let's look at the definition of the golden ratio. How to define a special number, we call it golden ratio. Yeah. You use 2 line segments. One smaller line segment, another longer line segment. Smaller one we use B, longer one we use A. Right? Yeah. So you put them together. Yeah. All right? Yeah. So then, look at the possible ratios we can get from these 2 line segments. Yeah. The first ratio, we can use A over B, the length of A line segment over the length of B line segment. A over B, the first ratio. Then you can get another ratio, different representation, ratio A plus B, the sum of these 2 line segments. Total length of these two line segments, A plus B, over the length of the longer line segment, B. Yeah. And ancient Greek people, they argue if these two ratios are the same, then that ratio is most natural. Natural. So they make that argument. Okay? Yeah. So that's the way we define the golden ratio. Later people call it golden ratio. Right? Yeah. But here, with this definition of the golden ratio, we want to find the expression. What number? What specific number corresponds to this golden ratio? So we need to solve an equation to find this golden ratio number. Yeah. All right. Let's simplify. Yeah. Because A plus B over A, we can simplify it as 1 plus B over A. Yeah. Our goal, we want to find A over B, that ratio, that number. Yeah. Yeah. It's not necessary to know A and B. How long is A? How long is B? It's not important. We only want to know the ratio A over B. Okay? Yeah. So then we introduce a variable. We use a variable X to represent the ratio A over B. Yeah. Then B over A, we can also use X to represent it. It's 1 over X, reciprocal of X. Yeah. In this way, we can get a one variable equation. X equals 1 plus 1 over X. Only one variable in this equation, so we have confidence we can solve it, right? Yeah. One variable, one equation, so we have the confidence we can solve it. Yeah. So let's solve it. Yeah. After simplification, yeah, we get x squared equals x plus 1. After the simplification, yeah, let's solve it first. Yeah. Next, because we know it's a quadratic equation. Quadratic equation, we can use this quadratic formula to solve it. Yeah. The general quadratic formula, A not equal to 0, there is a famous quadratic formula, x equals 2 possible x you can get. Yeah. So this is the formula, quadratic formula. Okay, yeah. Now let's get back to our equation with x, the meaning of golden ratio. Golden ratio. X is the golden ratio. It must satisfy this quadratic equation. Now let's apply the quadratic formula on the coefficients A, B, C. A1, B negative 1, and C also negative 1. Okay? Yeah. All right. Then, if we apply the quadratic formula, we get two possible solutions, 1 plus or minus root 5, then the whole number over 2. Yeah, two possible solutions. All right. But in this equation, we know x represents the golden ratio. Golden ratio A over B. Yeah. So let's recall, because yeah, in our golden ratio, x equals that line segment, the longer line segment over shorter line segment, A over B. It should be a positive number, right? X should be a positive number, golden ratio. But the second solution, 1 minus root 5, it's a negative number. 1 is smaller than root 5. So 1 minus root 5 becomes a negative number, then over 2, also a negative number. So it cannot be the golden ratio. The negative solution cannot be the golden ratio. So we should drop it. We drop the negative solution. Yeah. We only take the positive solution. And this number is the golden ratio. Approximately 1.618. Approximately. Because if you want to calculate, if you calculate the root 5, after the decimal point, there are infinitely many digits after the decimal point. Yeah. So it's an irrational number, not a rational number. Okay? Yeah. So no cycle. Rational number, you may find a certain cycle. So if infinite many digits after the decimal point, and here it's an irrational number. Golden ratio is an irrational number. Okay, irrational number, right? Yeah. Yeah. And we use a special notation to represent it. A shorter, simpler, special Greek alphabet, phi represent golden ratio. Yeah. All right. So then, yeah. Magic formula. So the last step, our goal, we want to derive a math formula for the Fibonacci numbers. Yeah. Here, let me write that formula first, using the golden ratio notation to write that magic formula. Yeah. What's that? F sub n, Fibonacci number with input parameter n, yeah, equals 1 over root 5 times parenthesis. Inside the parenthesis, the first term, phi to the n, minus the second term, negative 1 to the n over phi to the n. You can see, after we use the golden ratio in this way, we can get a Fibonacci number. And we know Fibonacci number, all Fibonacci numbers are integers, right? All Fibonacci numbers are integers. But from the right-hand side, phi, irrational number, phi to the n, also irrational number. It looks very messy, right? Yeah. The second term, also pretty messy, right? Yeah. Infinite many digits. Yeah. But then you do subtraction. After that, you do division by root 5. Then suddenly, you get nice integers. And those nice integers are Fibonacci numbers. Yeah. For that reason, we call it magic formula. Yeah. Because it's very hard. So if you can think about, if people want to guess Fibonacci formula, want to guess, make a guess, extremely hard, right? How can you make a guess like this? Right? Yeah. Almost impossible. Yeah. How can you connect to the golden ratio? Right? Yeah. Think about that. In this special way. Yeah. Yeah. Right. So a lot of story behind it. Yeah. So the next time, what do we need to do? Next time in part D, yeah. So we need to do these things, yeah, related to this formula. Yeah. First, we verify it. We want to verify this formula. Because if the formula is given, then verify if it is true or not. It's much easier than discovering the formula, right? Yeah. If you have no information, you need to discover the formula, then it's extremely hard. But here you do not need to discover the formula, right? The formula is given. This is the formula. But you need to verify if it is correct. So first thing we need to do, verification next time. After the verification, second part in our next class, we want to discover it. Because when you solve real world problems, nobody would give you some nice formula to you, right? Yeah. Most of the time you need to discover any formula you need to discover it. So our part 2, I will show you how to discover this formula. Okay? Yeah. So that's the part D on Thursday. Yeah. So then we will finish module 3. Okay? Yeah. After module 3, we will start module 4. Yeah. Okay. Yeah. All right, that's it.